Hello, my name is Niall Parent. I am musical designer of the Acxel re-synthesizer and Technos Vice President. You have just heard an Acxelized signal, that is, a sound resulting from the combination of a given number of time-varying sine wave oscillators. In this particular example, 207 oscillators have been programmed in order to simulate or reconstruct or resynthesize an audio signal. Resynthesis offers advantages not available with sampling. For instance, an audio signal can be transposed without changing its duration. So we start with the original, and then we can transpose it. In fact, with a sufficient number of oscillators, we can play two notes at once. We can also, thanks to resynthesis, compress the time or expand the time of an audio signal without changing its pitch. I am calling now a macro on the grapher, and this goes like that. And so forth. To better understand how this is possible, we first have to look at the synthesis power involved in the process of resynthesis. Starting with a sine wave, we are going to perform a few movements on the grapher which allows us to program in real time additive synthesis. This is the amplitude spectrum where I can in real time enter any frequency I want, any harmonic structure I want. Since the system uses parallel processing, it makes no difference for the Acxel to generate a given structure for one note or for more notes. In fact, in this situation, I could program in real time the amplitude of up to 512 oscillators. And so forth. Beside the amplitude spectrum, we need to be capable of varying the frequency of each oscillator by integer value. At this moment, I'm calling for synthesis cell number 2, getting rid of number 1, and then I'm calling for another macro, which we call the integer spectrum. In the amplitude spectrum, we control the amplitude of the signal. In the integer spectrum, we're going to control the frequency of the signal by integer value, and this goes like that. In other words, depending on the step size value selected by the user, any oscillator can be placed in the harmonic spectrum anywhere between harmonic function 1 and harmonic function 256. But we know that if we want to simulate, let's say, a clarinet of voice or the piano that we heard previously, we need these oscillators to be detunable. So I'm going to call back the amplitude spectrum like that, then call the integer spectrum where I say that few oscillators will fulfill harmonic function 2 and some harmonic function 4. And then I am going to call for another macro which we call the beating spectrum, where a fraction value can be entered, and again that is going to detune, in this case, 32 oscillators per note in real time. We hear the complex beating resulting from that macro. However, these features belong to what we call the fixed additive synthesis mode. In order to achieve resynthesis, we need more than that. We need what we call dynamic additive synthesis. Up to a certain point, we could say that resynthesis is identical to dynamic additive synthesis. In dynamic additive synthesis, I'm going to do a classical additive synthesis as we have seen previously, using, let's say, 4 oscillators. Let's say synthesis cell number 2, 6, 11, and 17, which at this moment stay to their harmonic to their pre-programmed harmonic function. But they could be varied, as we have seen, thanks to the integer spectrum. And now I am going to enter into the dynamic additive synthesis mode, which allows me to draw in real time a multi-segmented amplitude envelope for each and every oscillator. In order to avoid repeating the triggering of the note, I am calling for a full-length loop of that envelope, as you see there. And now I am going to draw the multi-segmented amplitude envelope for synthesis cell number 2. And we hear it as we do it. Same thing for 6. Same thing for 11 with beep beeps in it. Beep beep beep, we hear it. And 17 could be something like created an additive synthesis which is varying its amplitude in time. The next logical step, which of course involves an important computational power, is to have these oscillators to vary not only in amplitude but also in frequency. And I am going, with no synthesis compromise, to draw in real time multi-segmented pitch envelopes for these corresponding oscillators. Oscillator number 17, we hear it. Same thing for 11, then 6, then 2, and again. I have created a time-varying additive synthesis. If I go back to my amplitude spectrum and I get rid of synthesis cell number 2 and 6 and say 11 and keep only 17, what I have now is one sine wave oscillator varying in time. It varies in terms of frequency and in terms of amplitude. This time-varying sine wave oscillator is what we call one Acxel, Acxel being an acronym for acoustic element. There is an obvious relation between the Acxel and the pixel of the video industry. The Acxel, we could say, is the smallest audio element, musically significant, for your basilar membrane. If you know how to program very accurately a dynamic additive synthesis system, you should be capable of simulating any sound. What is it that you have to know? Well, you first must know how many oscillators are needed for simulating a given sound. Then you need to know what is the reference amplitude of each and every oscillator, which corresponds to the amplitude spectrum. You need to know also what is the reference frequency by whole numbers, that is the integer spectrum. You need to know what is the fraction value of the frequency of each oscillator. But most importantly, and this is the touchy part, you need to know what are going to be these numerous multi-segmented amplitude envelopes needed for simulating a given sound. Here, for instance, we are literally going to run through the internal life of a re-synthesized sound by looking at its successive amplitude spectrum. The other important thing you need to know is what are going to be also these multi-segmented pitch envelopes for these corresponding cells. And finally, since these frequency deviations may be different for each and every cell, you need to know what is going to be also what we call the deviation spectrum for a given sound. In short, supposing that I would have known how to program from scratch all of these data that I have shown to you, I would have been capable of simulating this. Which obviously offers the same advantages that we have seen previously. And so forth. Obviously, the previous signal was not programmed from scratch. The possibilities are so enormous that the feasibility of reaching that point from scratch is theoretical only. In reality, you would spend years and would never get the result we've got in a few minutes. So how do we get to the point where we can simulate any sound by the combination of time-varying sine waves? We have to provide a tool in order to give access to this simulation. The basic principle is that each sound is unique. Indeed, you realize that, for instance, if I make a very simple additive synthesis like I did, let's say with harmonic function 1, and let's say harmonic function 14 at a given example, the combination of that is a unique new waveform, a unique combination. Now, if this is true, the contrary is also true. That is, any sound is a waveform. And if it is true that a given combination generates a unique waveform, then there should be a unique combination for each and every waveform. The problem is to find that combination, which is where the analysis part of the Acxel system enters into the game. So here is what we do. We sample an audio signal and we store it temporarily. Once it has been sampled, we process it through a transform algorithm, a very complex one, based on FFT. We call this algorithm the Acxelization. What the Acxelization does is exactly to program the synthesis system that we have in the Acxel. In other words, it provides all the data that we have listed previously that we need for simulating any sound. Once this programming is finished, if we want to save the simulation of the audio signal, we simply flush away the sampling data, which from the musical point of view is not relevant anymore. We do not hear voltages. We hear a series of harmonics varying in time, which is a way to say that the Acxel system takes your auditory system as a model, or also, if you prefer, nature as a model, because we simulate it with a process, an auditory process, which is natural to us. Resynthesis offers a totally independent control of the frequency domain versus the time domain, which is why we can transpose without changing the duration, or time compress, or time extend without changing the pitch. But there is much more in that, and in fact much more important. The key aspect of the Acxel system is that once you have simulated a given audio signal, all of its components, that is, all of the Acxels and all of the parameters involved in the Acxel programming, can then be reprogrammed or transformed in real time. You hear it as you do it. In other words, resynthesis here is not the goal, it is the starting point. For instance, we have here an Acxelized piano sound, and we can call for its amplitude spectrum and play with it. We will discover, for instance, that on synthesis cell number 3 is located the fundamental, and that on 1 is a given subharmonic, and that we can play with it, change the color, and so forth. I could go on a second module where are located more of the high-pitch components, decide to control many synthesis cells at once. This is a preview of a technique which we call spectrumization, and I'm going to boost the amplitude here. Of course, I can also, for these corresponding synthesis cell, I could also change the frequency and so forth. So let's go back to where we were. We could take down the amplitude to where it was. I could obviously have done it directly by touching the grapher. I could call for could go on module 1, back to module 1, call it, say, the beating spectrum. I know that the fundamental is on 3, and I could literally and so forth. In fact, I could enter into more details. For instance, I will first correct my overall volume envelope, which is right there. That is the overall volume envelope. We will get back to that later on. And now I'm calling for the amplitude envelope of synthesis cell number 3 that I can redraw in real time, and I'm going to hear it as I do it. There we go. And so forth. Another thing that I could do would be to use the copy function, and by the copy function to create a chorus effect. This is an example where we have taken that same sound. You recognize we have modified it to fill in the harmonic spectrum a little bit, and then we have created with the copy function, as I said, a quadruple chorus. The result of that is that the sound now is getting obviously very different. We have put a large amount of fat, so to speak, to the sound, and this operation of copying a module as a whole was done in a few minutes. And then if I combine it, for instance, with the previous feature we have seen, like this one, well, I can say that in a few minutes I have created from an Acxelized sound what I call a Miami Vice type of sound. Resynthesis is not the goal, it is the starting point, which is why we have added to the Acxel an important number of synthesis and processing features which go far beyond resynthesis. For instance, each oscillator is waveform programmable. We can have a sound that starts with a sine wave, and we can move, let's say, to a square wave. Then we could move to a sawtooth wave, and we could eventually have a programmable waveform. At this moment, the waveform is identical for all 32 oscillators within a module, but they could all be different. Here is an example where we have a sound using an amplitude spectrum, an integer spectrum, a beating spectrum, which is why we hear that kind of jet effect, and a given waveform, which again can be programmed in real time. It goes like this. Another aspect is that you can also FM any signal. You see, the Acxel, from the moment it has Acxelizer sound, makes no difference between generating a simulation of any sound and a sine wave. It becomes an extremely powerful synthesizer. In this example, we have taken the previous sound you have heard, and we have added a little bit, very short FM onto it. So here is time, and this is the modulation index. And we can vary that in real time. As you can hear, if we want to have, let's say, to have the FM entering progressively like that, well, we can have it right now.